Hey everybody, so I wanted to look at a couple more problems from the AP exam today that deal with this topic we've been looking at. But I think I want to start actually with mice. Um, I think I want to start with mice. Where are my mice problems? Hello, mices. Hold on a second, I thought I had it up on the screen, but it seems to have gone away for a moment. Open recent. And no, I opened the wrong one. This is okay. So this one's called Mises. And if you look really close at that blurry picture, oh, maybe I could just save this document. There's that adorable tiny mouse holding a teddy bear. Okay, the rate at which the population of mice is changing, and notice that second word there, the rate. R of t, that's a rate function. What do I do with rate functions? That's right, we integrate a rate. T cosine 2t for time equals 0 to 90. These are days. And at t equals 5, there are 40 mice. Okay, so population of mice. So this must be mice per day because it's a rate. How many mice will there be after 10 days? See, part of me wants to say, well, if I just integrate that rate, I'm going to get the number of mice. And if I integrate from 0 to 10, won't that be the total number of mice? Well, the problem is that I don't know how many mice I had at t equal to 0. I'm told that the number of mice, the amount of mice at t equals 5 is 40. So I feel like really what I need to do here is think about an amount function. Now, I don't have the number of mice decreasing here, right? This is a rate in problem. This is not rate in minus rate out. If you want to do a subsequent problem that involves some sort of hungry cat, by all means, but our problem, I'm going to have that a of t minus a of 5 equals the integral from 5 to t of r dx. Okay? So when I integrate this function, I'm going to start at 5 and go from 5 to a certain amount of time. They want to know how many mice there are after 10 days. So that's a of 10 minus a of 5 was 40 equals the integral from 5 to 10 of r of t dt. Okay, yes, I did just switch from x to t. Why? Because these can't be the same. And now that I have a number there, I can go back to talking about t's here. Okay, so to find a of t, I'm going to add 40 to the value of that integral. Nobody's expecting you to integrate that by hand. This is with calculator. So, change my function. Y equals is now 10 sine t, close parentheses, cosine 2t, close parentheses. And we don't need this old rate out over here anymore either. All right, so what do we need to do? We need to integrate that rate from 5 to 10. So I'm going to y1, I'm going to pick that up with respect to x from 5 to 10. So this number here, minus 7.137, this is the change in population. Population of mice went down by 7.137 mice between day equals 5 and day equals 10. The hungry cat. Maybe the mice died. Maybe they moved to another place. I just know that the population went down by 7. And remember, that's a of 10 minus 40. This is that initial amount, or at least the amount at t equals 5. So when I add 40 to both sides, I can find the number of mice at 10 by adding 40. And so I get 32.863 mice. And How do I have 0.863? It was a terrible accident. I think it had something to do with a carving knife. Okay, so that's part A. Part B. Part B says, let P of t represent the number of mice after t days. Oh, P of t, P of 5. This is the number of mice function, what I was calling an amount function. Use an integral to express p as a function of t. Oh, we did that already. Here you go. That's part B. Part C. How many mice were there when the population monitoring began? What time is population monitoring beginning? Time equal to 0. So let's look then at, oh yeah, they said P of t, didn't they? P of t is going to be P of 5 plus the integral from 5 to t dx. Okay? And now we're looking for P of 0. P of 5 plus the integral from 5 to 0 of r dt. Now, you may feel uncomfortable with this, like, hey, I should pull out that negative and flip these. Yeah, the thing is, you're going to be integrating on your calculator anyway, so I don't think your calculator cares. 5 to 0. Okay, so math, integrate. We want to integrate that y1 function, not x min. We want to integrate function y1 in terms of x from 5 to 0. Okay, and don't forget to add. So that's going to be 0.649. Now, be careful, because this is now called a linkage error. This number does not represent this integral plus 40. This number represents that integral. Because I'm saying 40 plus that integral is equal to this number, these things are not equal to each other. I have made what AP readers call is a linkage error. Right. So, I know we often think about going along and going along and going along. No. If you have to, do that. Make an arrow instead of an equal sign. Because that arrow says this number comes from thinking about this. That equal sign says this is equal to all of that, and it's not. Now, if you remember to put that 40 in, that's great. Use that equal sign. So yeah, watch out for linkage errors. Linkage errors are actually really common in AP land. It's like the third or fourth most common mistake or type of mistake that kids make. Of course, more common are the mistakes where kid makes sign mistake, kid makes distributing mistake, or, this is a great one, kid answers the question they think is being asked instead of the question that's actually being asked. So, it's not a bad idea to go back and see, what was the question? How many mice were there when the population monitoring started? There were a little more than 40 mice at t equals 0 days. Good. And that's it. We've got our population of mice function, 40 plus that integral, and we use that to figure out how many mice we had at time equal to 10. Okay, that's very nice. See, those are the sort of things that we need to get comfortable with. Now, I don't think that is inappropriate for our test. Notice it was just a rate in. I was integrating a rate. These rate in, rate out problems, yeah, so with rate in, rate out, I think I'm going to say that's definitely where AP would like to take us these days. Okay? So, let's move on to this. I know that C of t is 27.08 e to the t over 25. And what is this? Well, T is years since 1980. Okay? And C is oil consumption in the United States in billions of barrels. Is the rate of consumption. It's billions of barrels per year. This is just the rate. 27 billion barrels per year. Oh my God, that's a lot of oil. All right, so here's the question. They say, find the total consumption of oil from the United States from 1980 to 1990. So, what am I supposed to do? Well, look, this isn't the number of billions of barrels of oil. This is the rate. It's billions of barrels per year. And what is it that I do with rates? I integrate a rate to get that amount. And we want to integrate from where? Well, years since 1980. 1980 to 1990. And again, I'm just going to do this on my calculator. I'm going to say the integral of 27.08 e to the x divided by 25, comma x, comma 0, comma 10. And the number I get here is 332.965 billions of barrels of oil consumed in the US from 1980 to 1990. Okay, that's a lot of oil. True that. All right. I'd like to look now at two more problems. This one is from AP exam in 2011. In 2011, this is also with calculator, but this one comes with a table, not a function. I'm given this table here, and we've got times. This is time in minutes, and this is H. That's degrees Celsius. Okay, we've got 0, 2, 5, 9, 10, and 66, 60, 52, 44, 43. Hey, so tell me, what do you expect to be true about this temperature function? Like, we have selected values here. Would you expect any of these numbers to be negative? No, I do not expect my numbers to be negative unless, like, I'm putting them in a freezer or something. This, by the way, is a pot of tea cools. The temperature of the tea is modeled by this differentiable function, h of t, on 0 to 10 minutes. And they say that, oh yeah, so I was asking about this temperature function. No, I don't expect temperature sitting, the T sitting on the counter to go to negative, but I also don't expect numbers in here to get bigger. The temperature of T isn't going to decrease, increase suddenly, and then decrease unless something happens. If it's just sitting on the counter, this is Newton's law of cooling, and the T is just going to continue to cool. Okay? Let's take a look at these questions. Use the data in the table to approximate the rate at which the temperature of the T is changing at time equals 3.5. Okay, so what is it that they wanted? They wanted the rate of change in the temperature of the T at 3.5. minutes. Well, that's kind of awkward because I don't have 3.5 here. But that's okay, because they said approximate. So all I'm going to do to approximate the rate of change at 3.5, right? They're saying find h prime of 3.5. Well, no, they're not. They're saying approximate h prime. Approximate the rate of change in the temperature of the T at this moment in time. And the way I'm going to do that is to use my average rate of change. I'm going to say h of 5 minus h of 2 over 5 minus 2, right? Because, look, 3.5 is actually halfway in between those. That's supposed to make you feel more at ease. H of 5, 52, h of 2, 60, and so I get negative 8 over 3. And what are the units here? Well, the units on h prime. The units on h are degrees Celsius, and the units down here, time, these are minutes. And so this negative 8/3 is going to be degrees Celsius per minute. Okay, show the computations that lead to the answer, but there's no justifying here. So there's my answer, good to go. Next, using correct units. Part B says, using correct units, explain the meaning of 1 over 10 integral from 0 to 10 h of t dt. Okay, well, h is a temperature function. Does it seem familiar? Does it look like 1 over b minus a integral a to b of x dx? Do you remember what that is? That's the average value of f on 0 to 10. So I want the average temperature across that 10-minute interval. That's what this is finding. This is finding average temperature on 0 to 10 minutes. We've got all these temperatures. And I just want to find the average of all those temperatures. Yeah? Okay, and what does it say here? Use a trapezoid sum with 4 subintervals to estimate this. Well, so they want the trapezoid sum for this. I'm going to approximate this integral by using trapezoid sum here. And they said 4 subintervals because I got 1, 2, 3, 4. Notice the subinterval width is not the same, so I'm going to have 4 different computations. I'm going to have 1/2, 2 minus 0, times base 1 plus base 2, plus 1/2, 5 minus 2, base 1 plus base 2, plus 1/2, 9 minus 5, base 1 plus base 2, 52 plus 44, plus 1/2, 10 minus 9, times base 1 plus base 2. Okay, now they ask us, use a trapezoid sum with 4 subintervals to estimate the value. Now, this is just this part. I can't tell you how many people in 2011 left this off. It's all of this divided by 10. Okay, so that's my value, and you can leave it like that. I'm going to be incensed. I'm going to think it's crazy. I think you need to tidy this up. But because College Board says it's okay, and our class is called AP Calculus, we're going to be okay with this. Yeah. Yeah, we are. Okay, so there's my average temperature on 0 to 10. Okay, third question. Third question says, evaluate 0 to 10 of h prime dt. Oh, but how am I supposed to do that? I only have h here. Well, remember, fundamental theorem of calculus, that's h of 10 minus h of 0. And what is h of 10? Well, 43. And h of 0, 66. And so I get negative 23 degrees Celsius. And so what does this represent? Well, it's a change in temperature from 0 to 10 minutes. So and it says here we're supposed to explain using correct units the meaning of this expression in the context of this problem. So I'm going to say the tea cooled by 23 degrees Celsius on 0 to 10 minutes. And luckily, this. Thank goodness for fundamental theorem of calculus. Okay, I got one last one I wanted to get with you today. This one. Yeah, this one. So this one is people in line for an amusement park. And the graph goes up, and the graph goes down, and the graph goes this way, and the graph goes down. This is 8, this is 6, this is 4, this is 2, and that's 0, and this is 1,000. And up here, we've got 1,200. This line occurs at 400. And I think that's all we need right now. Except that we need the pointers here. Okay. All right. So, and what is this graph? This is time in hours. And over here, this is people per hour. People per hour. This is a rate function. So let me read this one to you. It says there's 700 people in line for a popular amusement park ride when the ride begins operation in the morning. Once it begins operation, the ride accepts passengers until the park closes 8 hours later. While there is a line, people move on to the ride at 800 people per hour. The graph shows R of t. This is the rate at which people arrive at the line throughout the day. T is measured in hours from the beginning of operation. How many people arrive between 0 and 3? Okay, so 0 and 3. Well, this is the rate at which people arrive. That would be the number of people who arrived from 0 to 2. They want us to figure out 0 to 3. Well, wait a minute, I don't know what the value here is 3. Ooh. And you know what? College Board says it's okay, you know how to write the equation of this line. Look, this line has this ordered pair, 2, 1200, and this ordered pair here, 4, 400. So, what's the slope of this line? Well, the slope of this line is 1200 minus 400 over 2 minus 4. So that's 800 over negative 2, or negative 400. Now, I got a slope. I got an ordered pair. I should be able to write the equation of the line. Y minus 1200 equals negative 400, x minus 2. Or y equals negative 400x plus 800 plus 1200. And so I get y equals negative 400x plus 2000. Okay, and I want to know people per hour at 3. So y of 3 is negative 400 times 3 plus 2000, and that's going to be 800. So I know this value is 3,800. And guess what? They really just did do that. They really did just make you write the equation of that line. Okay, so our question here was how many people arrive at the line and show the computations that lead to your answer. Okay, so I'm going to say that this is a trapezoid. And so I get 1/2 2 minus 0 times 1000 plus the height here, 1200, plus this trapezoid over here, 1/2 3 minus 2, the heights are 1200 plus 800. That's the number of people who arrived. 2 divided by 2, that's going to cancel. It's going to be 2200. And this is going to be 1/2 times 2000. That's 1000. So I've got 3,200 people arrive during the first 3 hours. Okay, here's part A. Part B, is the number of people waiting in line increasing or decreasing at t equals 2? Justify your answer. Well, so here's the thing. I can do this problem 2 ways. And I should probably be comfortable doing this problem both of these ways, actually. So this is a classic rate in, rate out. So our amount at t minus our amount at 0 equals the integral from 0 to t of the rate in minus the rate out. Okay? We do this over and over and over and over. Now, what we want to know is the line getting longer or shorter between time equals 2 and time equals 3? So, I want to know if A, the number of people in line, is getting longer or shorter. I do know the number of people at time equal to 0. They said there were 700 people in line when we began operation. So now I could rewrite this as 700 plus this integral. Okay. Now I want to know if the amount of people is increasing or decreasing. So I want to look at A prime. That means I need to take the derivative here. Well, if I take the derivative of this number, I get 0. And the derivative of this integral is just going to be r in minus r out. Okay, so is r in minus r out positive at 2, positive at 3? I need to figure out what is happening at time equal to 2 and again at time equal to 3. And so I could say, well, I think because of this, no worries, I can know what about this line. But there's a much easier way. I mean, don't get me wrong, I love this amount function. And I love thinking about taking the derivative of the amount function, because you know what? They're going to do that to you. But let's annotate this graph. Didn't they tell us that 800 people were leaving the line every hour? So the rate in is above rate out. This, because rate in is greater than rate out, that means the line is getting longer. And I notice that that's going to be true, certainly from 2 to 3, from time equal to 2 to time equal to 3. Look at all these extra people who are showing up, and we're only servicing that 800. This number of people, they were able to get onto the ride. These people, no, not yet. And as a result, the line got longer and longer and longer. The line gets longer whenever rate in is above rate out. But correspondingly, when rate out is greater than the rate in, then the line gets smaller. Okay, and so I see that there's going to be this moment in time somewhere between 3 and 4 hours where, yeah, they serve more people than show up. And in fact, this number of people who show up, well, there's all this extra capacity. And what's that capacity doing? It's working on getting rid of all these people waiting in line because we can serve 800. Okay. So what am I going to say? What's my justification here? Because the question is the number of people waiting in line increasing or decreasing from 2 to 3? And I'm going to say that since R of t is greater than 800 on 2 to 3, the number of people in line is increasing. Period. Yeah, that's my justification. Just that there. Because the rate in is above the rate out, the line is getting longer. Okay, at what time is the line the longest? How many people are in line at that time? Justify your answer. Okay, so what do we think about that? Well, we know we're serving 800 people, and we know that there's this amount function, right? A equals 700 plus the integral from 0 to t of rate in minus rate out. And I know rate out is 800. Okay. In fact, I could even think about this as 700 plus 0 to t rate in dx minus the integral from 0 to t 800 dx. These are all the people, the integral, right? Integral of this is all the people who added to the line. We started with 700, we added these people. These are the people who got onto the ride and therefore got off the line, so we're going to take them away. And A. Now, what we want to know is when is the line when is the line the longest? So I need to find when A has a maximum. So A prime then is the derivative. The derivative of that is 0. The derivative of this is r of t. And the derivative of this, well, was just 800. Right? Because, there's no place for that t. This is, okay, this is just, yeah, no, that is my derivative. Okay, so what happens here? Well, if I'm looking for a max or a min, I want a prime equal to 0. And so I want to know when r equals 800. Well, that happens here. Okay, so how do I find that? Well, that's on this line again. What was that line? Didn't we go down 800 in, this was 2, this is 2. Oh, I think my original line, equation of the line was not right. Oh no, that was for finding this. We went down 800 and over 2, yes, that's minus 400 was our slope. And we said y equals negative 400 t plus 2000. Okay, and so if we plug a 2 in here, that's going to give us like 1200. Good. What about when does this line equal 800? So 800 equals negative 400t plus 2000. Subtract 2000, so negative 1200. Oh, duh. We know already. It's a time equal to 3. That's silly Billy. Okay. T equal to 3. At t equal to 3, we've got something going on. 3 endpoints 0, 8. Now, this is A prime. And what I know about A prime is positive from 0 to 3. The line is getting longer because the rate in graph is above the rate out graph. But from 3 to 8, I see the rate out graph is above the rate in graph. So that's a min. And that then is a max. Now you also have min and min. They didn't ask us about those minimums, but they did ask us to justify when is the line the longest and how many people are in line at this time. Well, we know that there are 800 people in line, and that's the longest line. It's very interesting. I'm surprised by that. Am I surprised? I think I'm surprised by that, because that's the rate equals 800. No, I don't know how many people are in line yet. I have to go back to the original function. Yeah, these are rates. These are rates, aren't they? Oh my goodness. That's correct. A minimum, a prime, 3. So I need to go back to a. Remember, a of t was 700 plus the integral from 0 to t of rate in minus rate out dx. And if I want a of 3, that's 700 plus the integral from 0 to 3 of r minus 800 dx. Okay, so this integral, well, you can't really see it here, but we've got some nice tidy boxes, and I'm actually going to find the area of each of those boxes. Each of those boxes has a width of 1 hour and a height of 200 people per hour. So if I multiply 200 people per hour times 1 hour, I get that each box is 200 people. And I want from 0 to 300. Okay, so 0 to 3. How many boxes are there? 3, 6, 9, 12, 13, 14, 15, 16. I get 16 boxes. So that's 16 times 200. Now remember, not only do we have these 16 boxes of people showing up, but we also have 800 from 0 to 3. So that's constant 800, 3 minus 0. Don't forget to add the 700 people who were already in line to your A of 3 computation. So what do we have? I think this is 3200 minus 2400, that's 800, plus 700 is 1500. So the line is longest, and I have to write the justification for this, so I better erase some stuff. Okay, the line is longest at t equals 3. The line is longest with 1,500 people because a prime is less than 0, no, greater than 0, at t equals 3, and a prime is less than 0, is to the left of t equals 3, and a prime is less than 0 to the right of t equals 3. I can use that same justification to explain. Don't forget, though, the answer isn't just this. They wanted to know what the longest line was, so we need that as well. Okay, finally it says write but do not solve an equation involving an integral expression of r whose solution gives the earliest time in which there are no longer people in line for the ride. Okay, so what do we want then? Well, we want to know when there's nobody in line for the ride. I want to know, remember we were thinking about this. These are all the people who arrived. And we were thinking about this. These are all the people who got off the line and onto the ride. I kind of want to know when this area and this area are equal. See, this is overcapacity. This is lots of people are being served who were waiting on this line. Like, we served these 800 people, but there were this many more who showed up. And we served 800 more people, but this many more people showed up. And so the line got longer and longer and longer and longer and longer until this point when the rate in equaled the rate out. And at this point we had our maximum line. And after that we've got this capacity, this excess capacity. And so I kind of want to say, well, this is how many people are in line at that moment in time. We said that moment in time was 3. And so I want to say when a of 3 is equal to the integral from 3 to t of 800 minus r dx. I think that would work. Let's see. This integral, rate out minus rate in. Yeah, I just have such a hard time in my brain doing that. I'm going to go with this because it's safer. So this rate minus this rate is going to be a negative number. Now, so either I want that or I want this, 800 minus r. Because on this interval, from 3 on, the 800 is above. So this is going to be some positive number when I integrate to some point t, and I want to stop when that number is equal to this number of people over here waiting in line. We calculated the number of people waiting in line already. We said that was 800. And so I could do this. I could eat that. I think I'm going to stop. It doesn't, there are lots of different ways you could write this. And that's the way I'm going to write this. Okay. So this would be when there's no longer anyone in the line. Okay. Well, yeah, nothing this hard on our test. So breathe and breathe some more. Yeah, breathe and breathe some more. But you will see this on the AP exam, and I definitely thought it was worth our time to take a look at this. Please make sure you convince Mr. Paz to go through the worksheet called Integral as Net Change, TCC, and Mice. You need to be comfortable doing those problems, and when you look at those problems, you'll understand why we just spent this time doing these rate in, rate out problems, okay? All right. Well, I hope you've gained some knowledge here. Feel free to watch these again, and remember, no rate in, rate out problems on this test, but by the time we get to that AP exam, oh my goodness, rate in, rate out, okay? And we'll practice it during our AP review. Take care, everyone.